working? It's not recording. I think that's recording. Okay. How are we doing with that, folks? We okay? Making progress? So make sure you've got all the solutions. So you should end up with a quadratic, so you're definitely going to end up with a pair of values for when you're doing the inverse trig. But then, depending on what the interval is, what is our interval? Between 0 and 2 pi, you're going to get 2 solutions for each of those. But also you need to, you need to make sure you're in radians as well. Okay. Now, what I'm going to do, because I think some people have started pretty well, some people might have gone off on slightly the wrong direction. Just make sure that everyone has a crack at it. And like I said, if some of you have gone off on the slightly the wrong direction, what I'd like you to do, if why is that not doing that? That's fine. Just to make sure you're starting off in the right direction, the first thing you need to do with this, look, we've got tan squared and we've got sec, so as we get more used to these, we will be looking for this sort of thing. We've got a tan squared here, and this is related to sec squared. So if we use that as a substitution, if we rearrange that and think, well, tan squared is sec squared take 1, we can write this as sec squared x take 1 plus sec x equals 1, and then you're going to be able to rearrange that to a quadratic equaling 0. You don't have to change it to cos yet. You're going to get it into a quadratic, you're going to factorize it, and you're going to end up with 2 solutions, therefore what sec can equal. It might be that they're both possible. It might be that you have to reject some of them. But that's kind of what we're looking at. So I'll give you just a couple more minutes. Some of you will be there. If you're there and you're looking at going, I'm absolutely confident with that. You could even check it. You could type in this y equals this and y equals that in your calculator and see where the intersection is if you've finished, or you can get it written up into your book if you've finished. But I just want to make sure everyone's got a chance to do that and restart if they need to, if they made a slight false start with that. Why is that? Okay, just another 30 seconds or so, and I'll go through the answers.
So I already answered one of my answers.
Mm-hmm.
It doesn't work with tan x.
How does it not work with tan x? Tan x? Oh, then hang on. So you're going to be doing the inverse tan though, aren't you? So the asymptote shouldn't. What have you got? What is it that you're trying to solve? You got tan x equals.
Oh no, I just had I've got some answers for each, but when I put it back into the equation, it doesn't work.
Oh, I see. I see what you mean. Because it's not valid for this. Oh, that's interesting. Let's have a look, because I hadn't spotted that. Might be the case. I hadn't spotted that being an issue, but let's have a little go at solving it. Right. So, where's that question gone? The range is the interval is 0 to 2 pi, but it's the domain. Rather, try not to use the word range for that. Range has a specific mathematical meaning that we'll meet later in the year. It's actually the domain that we mean. Right. So let's go through this one then. So what we're going to do is, like I said before, we're going to do a little substitution. We're going to say that we know that tan squared is sec squared x take 1. I've frozen it, haven't I? Sorry, I'm always doing that. And then plus sec x equals 1. So if I neaten that up, I get sec squared x plus sec x minus 2 equals 0. And then we can factorize that. If you want to do a substitution, if you want to say sec x equals u and then solve it in u, you can do, but I think most of you prefer not to do that. So we're going to have sec x and sec x. If it doesn't factorize, it doesn't mean it doesn't solve. You can always use the quadratic formula to help you solve it. And we need two numbers that multiply together to give minus 2 and add to give positive 1. So it's going to be plus 2 and minus 1, isn't it? Is that right? Yeah. That seems right, isn't it? So our solution is going to be sec x equals minus 2 and sec x equals 1. So now this is the point that we're going to change to cos. So we've got 1 over cos x equals minus 2. So cos x equals minus a half. And we've got 1 over cos x equals 1. So cos x equals 1. So we need to solve both of these. If we draw ourselves a little cos graph here between 0 and 2 pi, that is not a very good diagram. Hopefully you can draw better when you're not doing it on one of these funny stylus things that I've got. And for the first one, we're doing cos x is minus a half. So we're going to get this solution here and this solution here. If you do the inverse cos of minus a half, what do you get out? Sorry, 2 over 3 pi. So that's that first one there. How are we going to get that second one? So this is 2 pi over 3. How are we going to get that second one? 2 pi minus it. Yeah, by symmetry we can see it's 2 pi minus it. Or alternatively, we could have done that on the cast diagram. I'll do that over on this board because it's going to get a bit cramped if we go on there. So what's that going to be? That's going to give me 4 pi over 3, isn't it? To do that one on the cast diagram, what we would be saying is SATC. We are looking for a cos of a negative. So these are where cos is positive, the A and the C. So it's going to be in this one and this one. So it's going to be this obtuse angle here and this reflex angle here. This angle here is 2 pi over 3, which is going to be the same as this one here. So you do 2 pi take 2 pi over 3 to get this one. So you end up with the same angle of this diagram. Lovely. And then this one, let's do that in a different colour. Cos x equals 1. That's these points here, isn't it? It's this one and this one. So that is just going to be 0 and 2 pi. So hopefully that's what we got there. Hopefully that's making sense. Good. Sometimes you end up with things that you can't solve. So sometimes instead of having cos x equals minus half and cos x equals 1, if we'd end up with like cos x equals 3, that has no solutions. You need to explicitly reject it. So you need to say has no solutions or something like that. You need to not just forget about it. You need to show the examiner that you've recognised that that doesn't have any solutions and you've rejected it as such. Okay. We can get versions of this where, say, instead of tan squared x plus sec x equals 1, we could have had like tan 2x plus sec 2x and that sort of thing, and then we've got to do the same thing that we did last time of expanding our interval and all that sort of thing. But hopefully you can see this is really similar to questions that we had last year with sine squared plus cos squared equals 1. It's just now we've got 3. We've got the original, and we've got these new 2 identities to use. But we're looking for tan squared, sec squared, cosec squared, or cot squared. When you see those squareds, we can use those as a substitution. So if we do another one of these on whiteboards, let's have a look at. Yeah, let's do this one. Let's do one in degrees. There you go. Have a go at that one. If you want to on your whiteboard, you can do it. If you want to do it straight in your book, you can do for that as well. And like I said, you can check these on your graphics calculators. Make sure you're getting the right answer for that. But yeah, let's try this one. 4 cosec squared theta minus 9 equals cot theta. Really, really similar idea to what we had before, but this one was tan and sec. This one is going to be involved in cosec and cot. Have a little crack at that, see what you reckon. No, oh, sorry, that's worth saying. You don't have to remember those. You have to remember they exist and know that if you, oh, sorry, whoops. If you've got a squared, if you've got a cosec squared, or a cot squared, or a sec squared, you're probably going to use these. But what I would say is remember that and remember how to get from here to here, because they're so similar. It's really easy to go, is it cosec plus? Is it minus? Which side's the cosec on? Which side's the cot on? Is it cot with cosec or is it cot with sec? And just getting muddled up. And for the sake of just going, do you know what? I know I want tan in it. I'm going to divide through by cos squared, so I get sine of cos. There you go, I've got that one. No, you're not given them. So you do have to be able to obtain them from your mind in an exam. But I would say remember how to get from here to here rather than explicitly learning those two. Is a more reliable way of doing it. But yeah, you don't get them. Where Molly is today. Has an extra sinister edge nowadays, doesn't it? Ill or COVID ill? And Ted is awaiting his thing. If you finish those, if you take one past the rest on this sheet, we're going to just do a bunch of those on paper rather. I'll put the answers up in a second. If you could take one past the rest on those. The answers are on the bottom, but again, get in the habit of checking your calculator because you'll have the calculator in the exam. You shouldn't have the answers in the exam. Sorry? How are we doing, folks? Feeling all right about that one? Yeah. So I say this should be. I think they might have stopped near you. There's a pile of sheets there. Take one past first on, and then if you want to start on those, that's great. I'd say check it again. Have a check with the calculator. I'll put the answers up on the board. If anyone's stuck, let me know. Yeah, take one past first on. Sorry, there's a patch. If anyone, do you need paper or you? That's that. Sure.
Yeah.
Yes. I might not be able to do it today. I'm going to try and get it looked at. I've not had a proper chance to have a look at it. I've got a crazy day. Tomorrow I've got a couple of things. So if it doesn't happen today, I can arrange it for tomorrow. But yeah, it's a bit of a crazy day. And also I've not had a chance to do that. So I will try and best. But if not, I can do it while you're eating as well. So should be able to.
So I'm not really sure. I think I'm up on one.
Okay, what have you got?
50.36, 230.36, 348.335.
Yeah. What have you got as your 10 Peter equals?
1.207 and minus 0.207.
Yeah, no, you should get something that factorizes a bit more nicely than that. Yeah.
I think I might have gone the wrong way there.
What was your quadratic?
I didn't have a quadratic, I had a cubic.
Oh, yeah. How have you got a cubic? Because it's squared there.
I replaced the cosec with the 1 plus tan squared theta.
Yeah. And then it's a quadratic in tan.
And then I did 1 over tan, and then it times everything by tan theta.
Ah, you don't need to do 1 over tan. You rearrange it in cot. So you've got a quadratic in cot, so you solve it in cot. So I think something's gone wrong when you've multiplied through by the tan, which we can fix. If you show me your board, I'll see if we can figure out where you've gone with it. So you don't need to go to tan until you've got cot theta or something. So you say. Oh, hang on, you've done cosec 1 over tan. Oh, the cot. Oh no, so no, it is cot. No, it is cot. Sorry, I just can't read you. Oh no. Ah, you've got the. You've done the identity wrong. You've mixed up the two identities.
Yeah, right.
Yeah. So I'll put the answer up on the boards. So if you are getting stuck with it, you can figure out where you've gone wrong. This one we've gone for the cast diagram as the way to find the answers. But if you wanted to do it with a tan graph, you could just as easily draw a tan graph. You will get one solution here. You need to add 180 to it to find the next solution. Same idea with this one. You'll get one solution here. Add 180 to find the other solution. So it doesn't matter if you use the cast diagram or the diagram of the tan graph. So just a couple of things to point out with this. This time we've got cosec squared and cot theta. So we need to be using this identity here. But notice we don't choose, really, are we going to have a quadratic in cosec or in cot? We're kind of forced down that route because it's the cosec that's squared, so that's the bit that we're going to substitute for. We're going to change the cosec to 1 plus cot squared. We can't do something with a cot. We can't square root that identity. Well, we could, but it gets messy and we'd have plus or minus and that sort of thing. Go for substituting for this one. We get a quadratic in cot. We find the solutions for what cot equals, and then at that point we change it to tan. If there's any we need to reject, we do reject, but actually for tan you don't need to reject any. And then we get all the solutions in the given interval, making sure we are in degrees. So like we said before, as soon as you read the question and see it's in degrees, you should be changing the calculator to degrees, so you don't get all the way to the end and go, meridians. So do make sure you're doing that. And some of you may have already seen, it's very easy to get confused with these identities because they look kind of samey. Sometimes it's +1, sometimes it's -1, depending on how you've rearranged it. They look very, very similar. You don't get given these, and there are things that I'd urge you to remember and things that I'd urge you not to remember. I would not remember these explicit formulas. I would remember how to get from them to this one. Because all you need to do is say, if we're looking at that one, say, I know I need the one with cosec squared in. Well, cosec is 1 over sine squared, so I'm going to divide through by sine squared. So I need to do this one. I'll divide through by sine squared, I'll simplify it, or there's my identity. It's not a lot of work in the exam, and you're not kind of second guessing yourself, right? Is it plus, is it minus on this one? Is it cosec with the cos, or is it cosec with the tan? I think it's safer to do it that way. Okay? Wonderful. So we'll do maybe quarter of an hour, 10, 15, 20 minutes. We'll see how we feel about them. You should each have now exercise 3D. Questions are at the top. I think, well, maybe they've not quite filtered their way to here. There we go. There's the answers at the bottom, but I'd recommend at least for some of them, check they're using your calculator, if not all of them, just so you're practicing that skill as well and getting used to doing that. Because actually, it's practice of solving trig things, but also is practicing solving intersection of graphs as well. So it's really getting you confident with it. It's also, if you're switching between degrees and radians, getting you used to doing the V window thing, where you adjust the scale of your graphs, which for some people is initially a bit intimidating and they don't like fiddling with those numbers. The sooner you get over that and just kind of like, oh, I'll just change the axes, it's fine, the better. So I'd really encourage checking with your calculator. Right. The first one, okay, it's the first one. We've got 2 cos squared minus okay. So with the homework. So with that one,
Yeah.
you can do it as a if you look at what we're aiming for.
It's just
We've got causes and sines in there. And we haven't got the +1. So what you could do is you could change that one for a cos squared plus sine squared. Equals 1, doesn't it? So you could do it that way, or you could look at the left-hand side and say, well, I've got 2 causes for that. So if I take one of the 2 cos squares, right? If I take one of those cos squares and change it to a minus sine squared. So I added those. The first one actually, question 4 on this one is a little bit weird and actually relies a little bit more on this than these ones. It is worth doing. But if you want to do some of the other ones first and then return to question 4, because I think they're trying to ease you into it by having a sine and cos rather than sec, cosec, and cot. But actually, I think in some ways it's a little trickier. So if you want to try some other ones first and then go back to question 4, that's absolutely fine. All right.
How long did you say the test was going to be?
I'm just going to add up the points now and just check. Yeah. Yeah, if you want to skip that question 4 and come back to it, I'll give you a hint with it in a second. But if you want to do some of the others first, because that is not typical of the exercise, but not really what we've just been practicing. It's related, but.
Sorry, do you have any of those sheets?
Oh, yes.
Oh, yeah.
You pass them on too eagerly.
Oh, no, I think it was, I got 3B for some reason.
Oh, sorry.
I don't. Yeah, hour and a half, so 75 marks. Yeah. So I'm confused with question 5. So, what have you done?
Fair bit, but
Yeah.
I'm checking the sign. So if you're
So take me through line by line.
So the sec squared x,
Yeah.
change that to 5 lots of tan squared x equals 1.
Was there a bracket?
Yeah.
Lovely.
Plus
expand
tan
that?
squared x. Yeah, then I expand it to 5 tan squared x plus 5.
Yeah.
Plus 2 tan x. Just
Yeah.
tan squared x, and then took away the 5.
Yeah.
Combined the, so you got 8 tan squared x equals 4.
Yeah.
Tan squared x equals 4.
Yeah.
Sin squared x cos squared x equals.
Oh, you can just square root of 4 over 8. Well, 4 over 8.
Oh, okay. So then, yeah.
So tan x is plus or minus square root of 1.
Okay.
Yeah.
And then, but then it asks.
Oh, does it want to sign up? Oh.
Then it asks for sin x.
Which one is this? This is number 5, is it? The possible value sign.
Folks, there's a little twist on question 5 that I want to show you. So if you know what tan theta equals, and it wants an exact value for sine theta, because we've not done one exactly like that. You could do it on your calculator, but actually it's better to do it with without to do it with hang on, sorry, I want to get if I get actually I'll do it on there. There we go. You can do it using a little diagram. So if we know, so if I draw a little right angle triangle like that, so say I know that, I'm going to do a different triangle to what you get there. Say I've got, if I know that sine theta is opposite over hypotenuse, isn't it? So if I am told that sine theta is 3/5. So say you did some working out and you found out that sine theta is 3/5. We can draw a little right angle triangle like this, where the opposite is 3 and the hypotenuse is 5. And then we can work out the missing side there. We can work out the adjacent, because we can just do a little bit of Pythagoras. So in this case, it would be 4, because I deliberately chose nice numbers. Okay, but even in the question, it might be nice numbers. If it's not particularly nice numbers, you'll end up with a surd, and that's fine. The surds aren't particularly horrible. So what we've got there then is we know that cos theta equals, cos is adjacent over hypotenuse, isn't it? So cos is 4/5, and we know that tan theta is opposite over adjacent, so it is 3/4. So once you know one of them, you can draw a little right angle triangle and you can get all the others as exact values. But we also might need to think about, well, that's one solution. We've really only dealt with if they're in this top quadrant here. So if we were given this, if this is, sorry, not that one, if we started with sine theta is 3/5, if that's what we were given originally, we don't, unless we're told otherwise, we don't know if that's acute or obtuse, or we don't know what that is. What we do know though is if sine is positive, so sine is positive, so we know we're dealing with this quadrant and we know we're dealing with this quadrant, which means our theta is either acute or obtuse, which means say we wanted to find cos theta, we would know that we could have cos theta in this quadrant. So we could have cos theta equals 4/5. But we could also have it here as well, where we're trying to find this angle here. This angle here is going to be in this quadrant, and in this quadrant, cos is negative. So cos theta could also equal minus 4/5. So if we're not told the angle is acute or obtuse or reflex, if we don't know which quadrant it's in, we have to consider, well, just because sine theta is positive, just because sine theta is 3/5, it doesn't mean that necessarily cos and tan are positive as well. So we can get the exact values in terms of 4/5 and 3/4. If we don't know exactly what quadrant it is, it could be positive or negative. If it said sine theta is 3/5 and sine is obtuse, then obtuse means it's between 90 and 180. We know we're in this quadrant. We know only sine's positive there, so then we know that cos theta will be minus 4/5 and tan theta will be minus 3/4. If we're told sine theta is acute, we know it's in this quadrant here, so we know cos is positive 4/5 and tan is positive 3/4. So for number 5 there, you can, if you want to, work out the values of theta and or values of x rather, and sub them back into sine theta. But it's easier once you know what tan is. It isn't tan, isn't it? Yeah. Once you know what tan is, draw a little triangle. You know the opposite and adjacent, work out the hypotenuse, and from that you can work out what sine is. But you need to consider, can it be the positive and the negative? Does it have to be positive? Does it have to be negative? The easiest way to do that, that's where the CATS diagram comes into its own. You could draw the diagrams and kind of go, oh, this graph is above the axis, this is where this graph's below the axis, and that sort of thing. I think the CATS diagram is the easiest way to do that. Right?
Yeah, on just what you said. So I did that.
Yeah.
But I'm a bit confused as how so
So
you can eliminate if it's going to be both positive.
So this is number 5, isn't it?
Yeah.
Now, we don't know anything about the tan, do we? We're not told, sorry, about x. We're not told x is acute or obtuse or anything like that. When you do it, you end up with tan x, and in fact, in this case, you get tan x equals plus a half and minus a half, don't you?
Yeah.
So actually, because of that, when you find the sine and cos, it will be positive and negative, because it's going to cover all the quadrants, because you're going to get 2 solutions where tan is positive and 2 solutions where it's negative, and some combination of those solutions will give you the positive and negative sine and cos. Say it didn't do that. Say it ended up with just tan x equals a half. Well, for tan x equals a half, that can be true here, and it can be true here. So if it said tan x is greater than 180 degrees, so if in the question it says it's a reflex angle, so we know it's a reflex angle, we just don't know what it is, and you work out that tan x is positive, you'd know that it's in that quadrant. So as soon as you know that it's in that quadrant there, you know that sine and cos must be negative, because in that quadrant only tan is positive. If it said tan was acute, and you worked out that tan x was a half, then you know you're in this quadrant, so sine and cos would have to be positive, because everything's positive in that quadrant. So you need more information than that. If it's saying, look, it can be anywhere, because you'll get 2 solutions out of it in an interval between 0 and 360, one of those will lead to a positive sign, one will lead to a negative sign. And
so does that mean you're going to end up with 4 solutions for x?
You would end up with 4 solutions, but you will only end up with 2 solutions for sine and cos, because there'll only be the plus and minus of whatever you worked out from your little triangle. But there would be 4 solutions if it actually asked you for x rather than sine x.
Right. Okay.
Because if you think about that on the graph, if you're solving a tan for something positive and something negative, you've got those 2 and you've got those 2, haven't you?
Yeah.
So that's 4 values of that. But if you think about the sine graph in that interval, what you'll have is this one would lead to this. This one would lead to this. So these 2 would both be positive. This one would lead to this solution. This one would be this solution.
Okay.
So you'd end up with 4 solutions. There'd be those same 4 values of x.
Yeah.
But some of them would lead to a positive sign version of the same magnitude, same size number, but some would be positive, some would be negative.
Okay.
Right. we will in maybe 3 lessons time. We will do one that's really focused on the CAS diagram.
Yeah, I'm actually going to doing it.
It takes once you get used to it. And I'll be honest with you, when I was at school, I never really liked it. I could kind of do it, and I kind of cheated with my calculator because I could always check.
Yeah.
But it didn't click with me for a long time. And I clicked with the graphs later. I didn't see the graphs until much later. I was like, oh, now I get it. And now returning to CAS diagram, I'm a lot happy with it.
Yeah, that diagram is the top left.
Yeah. But the CAS diagram is basically taking the when is it above and below and putting that in a handy diagram. Okay, folks, can we just concentrate? So I want to make sure you've got a good practice of this. These are really common questions. It's also helping with your solving trig stuff that will be in the test. So the sec, cosec, and cot won't be, but this sort of thing with sine, cos, and tan may well be. Okay, which one are you stuck on?
Number 5. I still don't understand like the cos diagram.
Okay, so have you got to tan theta equals, excuse me, plus or minus 1 over root 2? Yeah, okay. So what that means, what you could do is you could do the inverse tan of that, and you could, once you've got the inverse tan of that, you could find the different values of x and sub them in sine theta, and you get answers out that way. What's the slightly more elegant way to do it is to go, do you know what, I'm going to draw myself a little right angle triangle. I'm going to work out the hypotenuse from that, because I know the opposite and adjacent, and then I know at least the size of the number. So when you do that, you're going to get...
I did that with root 3 as a hypotenuse.
Root 3 is the hypotenuse. So what did we want? We want sine, so sine's opposite over hypotenuse. So what was your opposite?
So I got 1.
So you get 1 over root 3. So we know the size of sine theta is always going to be 1 over root 3. But what we don't know, so if you imagine that being up here, like, we don't know if it's going to be positive or negative. So it depends on the value of x. Because we don't know whether we've got an acute, an obtuse, or reflex value of x, actually it can be both in this case. Because we don't know which quadrant it is. We don't know if x is between 0 and 90, between 90 and 180, between 180 and 270. In fact, because we're listing all the solutions, it can be all those things. All of those are valid solutions of this. Because they're all valid solutions, it can be the positive one and the negative one. If there was more information in the question, if it said x is, between 0 and 180, for example, when you did your tan one, if you're looking at between 0 and 180, well, it can be in this quadrant or this quadrant. In this quadrant, everything's positive. So for that one, it would be when tan x equals positive 1 over root 2. For this quadrant here, only sine is positive. So this would be when tan x equals minus a half. Okay.
Yeah, I just don't.
So what that means is, because sine's always positive here and everything's positive here, if you knew the answers were between 0 and 180, regardless if you're trying to solve tan x equals 1 over root 2 or minus 1 over root 2, your sine would always be positive. And if you look at the graph, that's true, isn't it? Between 0 and 180, sine is always positive. So it could only have those values. If you were told it was between 180 and 360, well, it'd have to be in this one here and this one here. And actually, for neither of those, sine is positive. So sine would have to be negative. If you were told that that would be anywhere between 0 and 360, which is what we've got, well, if it's in this quadrant, sine would be positive. If it's between 0 and 90, it's positive. When x is between 90 and 180, sine is positive. Between 180 and 270, sine is negative, and between 270 and 360, sine is negative. And you can see that from the graph. Positive, positive, negative, negative. So because we're doing it between 0 and 360, sine could be all right.
Yeah.
Oh, no, that's fine. That's absolutely fine. What am I doing? Everyone good? We happy?
Yep.
Cool. Should we say about 5 more minutes just to get to the point where you kind of like, yeah, I can do these. You reckon that'll do it?
Yeah.
Wonderful. Right, I'm just going to print something off for the next bit. I can teach this.
So just what? Yeah. Oh, it's just
That's saying what x equals. So if it's in the brackets, it would be this one plus 1. It's a 1 can be right, because you know when there's a solution, when it's
Oh, I know how you've done that. Yeah, it's so stupid, but I know.
You know Cole's cross.
Yeah.
I remember there was really one way because I was like keep heading east, I'll get there eventually.
That is so easy. You know it's burned. You know.
Pine chips.
Yeah.
Do you want to go? I didn't know comes off. Can you go for sure? Nah. I didn't think we probably shouted to you, so I got in and I was like, well, from warm. Such a cat. You don't think no, you can't just choose that.
Oh. Parrot, like, yeah, parrot.
Just landed on the head.
Yeah. It is.
Oh my god. Where did it come from?
Yeah, it's in Brazil.
How are we doing, good? Ish. Okay, I'd really like to see some diagrams, whether it's a class diagram or a sine, cos, or tan graph, so I can see how you're working out those extra solutions. Make sure you're getting those right.
Yeah. No, like. Oh, right. minus 13. Why are there 4 solutions?
Too many things. I'm sure this was fine. No, that's a different song. I think it goes. Last but not least, easy question. The problem is the easy questions are going to ask. They're more hard.
How are we doing, folks? You all right?
I've got a question, sir.
Okay.
If I've got tan 2x equals 2,
Yeah.
do I have to discard it?
Ah, yes. Well, no, not for tan, because tan could be anything, can't it?
Ah, yes.
If it was past 2x equals 2,
Right.
yeah, you'd discard it, absolutely.
So,
But do be careful with that, because remember, you need to wait till it's in sine or cos. So don't go too early with it, because if you've got cosec equals 2, well, that means 1 over sine is 2, so sine is a half.
yeah.
So if you're used to kind of looking at anything bigger than 1 or smaller than that, more negative than negative 1, go, oh, I reject it.
Yeah.
But because we're dealing with reciprocals, actually it's the other way around. So yeah, don't go too early. Okay, where's that? Oh, okay. So she still has the summer work, and you're not going to get the test, any feedback on the pre-test work, can I? Okay, can you make sure you bring them in tomorrow? We've got a lesson with this tomorrow. Don't know. Okay, we'll bring them in anyway, because you can always give them to me in the illustration. You need to bring them in to so we can create the right, if you... We have,
Yeah.
oh, no. Yeah, for 12, the interval and the solutions they've got don't match up. It looks like they've done it between 0 and 360. Oh, that's annoying. You can, if you've done it between minus 180 and 180, check out your calculator. If you've done it between 0 and 360, you can check the ones from there. Yeah, if you want to finish up the one you're doing, because I think hopefully you've got the hang of it now. Finish up the one you're doing, and then what will, if you grab the whiteboard out from before, we're gonna do a little bit of shenanigans on whiteboards.
Did you got any scissors?
I do.
Okie dokie, we all nearly there, getting to the convenient points. Cool. So what we're going to do is we're going to have a little look at the sort of prove that and show that question. So similar to what you had last year, you met ones where it was like prove this identity is true. We're going to do exactly the same sort of thing, but we have now got more identities that we can use. So we can still use sine squared plus cos squared equals 1. We can still use sine over cos is tan, but we can also use these two as well. And by the end of the year, we're going to have another bunch of identities as well. We're going to meet something called the compound angle formulae. We're going to meet double angle formula as well. Okay, so we're going to have a load of them, but the strategies for doing these are going to be the same. Before we do that, though, there's a skill we need to just practice on the whiteboards, which is a little bit of manipulating fractions that, while you might have seen this before, it's a little bit, in a way, it's a little bit niche, because it is just manipulating fractions with a GCSE sort of skill, but you don't often get asked this sort of thing at GCSE. So we're going to do a little bit of playing around with this on whiteboards first, because when we're dealing with sec, cosec, and cot, we're often going to end up with fractions within fractions, and we need to be able to deal with fractions within fractions. So, on your whiteboard, if I gave you this, if I gave you a half over 3, can you neaten that up so it's not some horrendous triple-decker thing? So it's a half divided by 3. So if you want to think of it as a over b, where a equals a half and b equals 3, that's an easy way to think of it, that's fine. Or you can just look at, there's my big line. There's where the line separating the two things is. A thing that I only learned a couple of years ago, that line is called a vinculum. Never needed to know it before, found it on Wikipedia. Numerator, that came out wrong. Numerator, denominator, vinculum. There you go.
That doesn't need to be named.
It doesn't need to be named, but it's quite nice knowing it. Right, okay, so 3, 2, 1, let's see what you've got. Don't worry if you're not sure, because it is a little bit weird. Excellent. Most people got it, it's a 6. The reason it's a 6 is because that means a half divided by 3, which is a half times a third, which is a half, half times a third is 6. Okay? What about if it was the other way around? What if my big line, my vinculum was here? That sounds a little biological there. When I said it was my vinculum, that didn't feel entirely comfortable.
How do you know that sometimes it doesn't really have a big line?
Yeah, you will know in the cases that we're dealing with because of what happened beforehand. And I think usually we'll have that. If you're just given something like that, it's ambiguous. You can't tell. If you're just given like 3 over 4 over 5, who knows? That could be either, and that's bad maths on behalf of the person that's got you to there. Okay, so 3, 2, 1. What have we got for that one? Oh, brilliant, brilliant. It's 3 over 2. The reason it's 3 over 2 is because we do 1 divided by 2/3, which equals 1 times 3 over 2, which is 3/2. Lovely. Let's stick with numbers. We're going to go algebraic in a minute. Let's stick with we'll go hybrid. We'll go numbers and letters. We'll go for, what about this? What would you do with that? 1/x plus 2/5. Okay. 3, 2, 1. Let's see what we've got. Yeah, this one was a bit more divisive. Okay, right. Let's. Oh, unmute. There we go. Let's do it on here so that I can share it with those that aren't in. So, what was the actual question? 1/?
It was 1/x plus 2/5.
Well, it was 1/x.
Yeah, so 1/x plus 2/5. Yeah. Not 1/x plus 2/5. 1 plus x.
Yeah, that's
1/x plus 2/5. Yeah. Right. So what I would do with that one, what I would be tempted to do with that one is think about equivalent fractions, because if you multiply the top and bottom fraction by the same thing, it's an equivalent fraction, so a half is the same as 2/4. So we want to get rid, well, not get rid of this, we want to stop it being a fraction. So if we multiply this by 5, that'll get rid of the denominator there, won't it? So if we do the bottom by 5, we need to do the top by 5. So what we're going to end up with is 5/5x plus 2, like that. Is everyone happy with that?
Can you do it like just put the 5x, so just times the x by 5, wanting so it's a fraction, wanting divided by that.
Say that again. So I've got 1/x plus 2/5. You're saying,
So I just made the fraction and wanting the whole fraction. Like that. And then
like that. Yeah, you can do that. Yeah, you can add the denominator together. You can say x plus 2/5 is 5x plus 2/5, and then you could say that's the same as 1 divided by that, which is the same as 1 times that. Yeah, that's fine. Yeah, I think that's probably a little easier, but yeah, nothing wrong with that. Let's do another one like that. How about this? How about if let's just move the position of the x around. Let's do 3 plus 2/x like that. What about that one? What do you reckon? Okay, 3, 2, 1. Let's see what we've got. Yeah, now everyone's on board. So multiplying top and bottom by x. If we multiply top and bottom by x, we get rid of the fraction. We get x on the top. Well, we don't get rid of all the fractions. We get rid of the fraction within the fraction. We get 3x plus 2 on the bottom there. Oh, sorry. Thank you. I don't see that stopping anytime soon. That's going to be a continued feature of the lessons, is me yammering on when it's on freeze. Let's have a look at something like this. How about if we've got x plus 1/3 and x take 1/2? On your whiteboards, have a go at that one. Double fraction within a fraction situation. feels it's going to be some kind of
Because I saw it was deck.
kitten being in pain. That feels like an illegal manoeuvre going on over there.
I've killed something.
Okay, let's see what you've got, folks. Let's see how you do. Okay, good. Okay, so, what you absolutely cannot do, don't even consider doing this, is cancelling the x's out. Okay, you can't do that. The reason you can't do that, if we imagine them being numbers, if you've got something like this, if you've got, let's do, if you've got 10 plus 1 over 10 plus 2, that is 11 over 12, isn't it? What is not is a half. Okay, put a dead puppy on the pile. It's a sad day. Don't do that. Okay, so what you can do, however, is we can think, how can we get rid of those denominators? How can we get rid of the third? How can we get rid of the half? And you can do it in 2 steps, or you can do it in 1 step. To get rid of that third, or to get rid of the denominator there, we would multiply by 3. If we do that to the bottom, to the top, we have to do it to the bottom. To get rid of the 2, we're going to have to multiply by 2. So we're going to have to multiply top and bottom by 2. In other words, if we multiply top and bottom by 6, we've got rid of those fractions. So what we will end up with is 6x plus the 3 cancels with the 3, so we have 2 there, and 6x minus 3. Now, at that point, still don't be tempted to cancel that 6 and that 6x. It's still not okay to do that, okay? Stop there. You're done. Right. We're going to do a couple more. Did anyone want to put any of those, a little note about any of those? If you're happy, you don't have to, but just in case you want to. Right. If no one wants to, let's do, what should we do this time? Let's do this. Let's do 2/3 over 4/5. We've gone bonkers. We've got a stack of them 4 numbers high.
You ever get like 5 numbers high?
You might do, but that tends to be, because that's like just you're substituting 2 fractions into a over b. So that's kind of sensible that you might come to that. Or the one that we did before, where it's a constant plus fraction over a constant plus fraction. To get 5 high, you're kind of substituting into something that's already stacked fractions. So you could probably simplify it before you get to that. So you could, but that tends to be the peak of it. Okay, this one might actually be easier than the previous ones. What do you think? Because this is just 1 fraction divided by another, isn't it? This is just 2/3 divided by 4/5, which is 2/3 times 5 over 4, which is, you can simplify before you multiply if you want to, or you can do it, so you can say it's 10 over 12. It is KFC, so it's 5/6. Okay, now, the reason we're doing this, the reason we did this as a little diversion, is because we need to be able to do all those sorts of things with sine, cos, and tan. So if we've got something like this, if we've got 5 over 1 over sine x, which we might get from doing, if we had 5 over cosec, then we could change the cosec to 1 over sine x, and we'd end up with 5 over 1 over sine x. And it'd be clear where the big line was, because we started with 5 over cosec, so we know that that big line is between the 5 and the 1. It's not between the 1 and the sine x. What would that rearrange to? It's 1 over sine x. There's no.
Like physics.
Oh, that's just a residual smudge. Okay, what do you reckon for that one? 3, 2, 1. Lovely. Good. Lovely. So yeah, 5 sine x, or if you wanted to write it as 5 over cosec, you could, but that's kind of going backwards to where we'd be doing it, because it's saying 5 divided by 1 over sine x which equals 5 times sine x over 1, which is just 5 sine x. Oh, I could have done that more neatly, but never mind. Right, how about this? Let's do this one. Let's do 1 over sine x over 1 over cos x. In other words, we're doing cosec over sec. So 1 over sine x over 1 over cos x. And you can think of, actually, I'll say that in a minute. Okay, what have we got for this one? What have we got for 1 over sine x or 1 over cos x? We've got, cos x or 1 over tan x. With both of these, with this one and this one, you can think of it as a KFC thing, or you could think of this as being times top and bottom by sine x. So if you times that by sine x, you get 1. Times that by sine x, you get 5 sine x. This one, you could think of it as timesing top and bottom by sine x cos x. Or you can think of it as a KFC thing. It's up to you. I think the multiplying top and bottom definitely comes into its own when you've got a sum involved. But for these ones, KFC I think is just as easy. But it's absolutely up to you as long as you're getting the right answer with it. 1 over sine x times cos x over 1 equals cos x over sine x. Or if you wanted to write it as cot x, you could do.
Would you, are you always able to do KFC on ones like that?
On ones like that, the ones that you can't do KFC on is well, you could do like Rude did before. If you could add those two things together, you could add the 3 plus 2x, get it all over one denominator, and then KFC. But I think this sort of leaps ahead as a method.
Especially for the size, like you'll most of the time be able to do
Yeah.
KFC.
So, yeah, if it's just one big stack, then KFC kind of helps you out. So if we've got something like this, how about this one? 1 over cos x over sine x over cos x. So that would be equivalent to if the step before that might have been you were given sec x over tan x. So you're starting with something that looks relatively neat, sec x over tan x. You go to this, it looks a bit horrible, but there might be reasons that we want it in terms of sine and cos. What did you get with that one? One over cos x all over sine x over cos x. Okay, what have we got for this one? Yeah. A few people writing it in slightly different ways, either 1 over sine x or cosec x, because we've got 1 over cos x divided by sine x over cos x. And then nicely, when we change that to multiply, we get the cos x's cancelling. So we get that cos x cancelling with that cos x there, and we get 1 over sine x. Which if you want to write it as cosec x, you can do. Okay, last one or two. Let's go back to the ones where you've got sums involved. So let's do something like this. Let's do 6 over 3 plus 1 over sine x. Yes, they were originally. Because I knew what was coming next. Yeah. It's one of those things because it's kind of GCSE in terms of its manipulating fractions, but you never really get.
Sine and x.
Yeah. But actually, once you build up to it from the numbers, so it's fine.
It's fine now. I can do it all now, but like back when I didn't know what was happening, so it was just like, yeah.
Yeah, so I think this is one that I wouldn't care to see. I'd multiply top and bottom. How are we doing with this one? What do you reckon? Okay, yeah, good, good, good. So for this one, we want to get rid of that sin x, so we'd multiply top and bottom by the sin x. Get rid of that denominator. You have to do the same. We have to multiply top and bottom by the same thing. So you get 6 sin x on the top, and we get 3 sin x plus 1 on the bottom. Happy with that?
Is that it? Is that all you do?
Yeah, you definitely can't cancel that sin x with that sin x without getting in trouble.
I thought I was doing.
Yeah, good. So last one. Let's go for. Oh, I've run out of blank slides. Hang on. Let me just put a new blank slide in.
What is it? Everything from last year.
No, did you do the pre-test? It's on that stuff. The pre-test is a pretty good
Is that a
gauge of. It's largely stuff in the sum work. I think there might be some slightly different. The pre-test, the homework. The
Pre-test is quite similar
revision
to some
homework.
of them.
Yeah.
Wait, so is there anything in the test that was in the pre-test?
Only in the sense that I've not looked at it for a while, but say there was a connected bodies one, and you've done it on if say the sum work was on a vertical pulley, it might be the one in the test was a horizontal pulley, or it might be a tractor question or something like that. So topic-wise, it's the same, but it's not necessarily exactly the same question. Yeah, kind of thing. That in that sense, it might be different or it might be the same. Right, let's have a look at this one. Let's go for sin x plus 1 over sin x all over. Let's do this. Let's go for cos x. Oh no, we'll do sin x. We'll do sin x as well. We'll do. Oh, actually, yeah. Let's do this. Let's do sin x minus 1 over sin x. Let's see what happens if we do that. Actually, no, I'm going to slightly change it. Sorry. This might work. This might be a nice question. Here we go. Yeah, let's do that. Let's do it. Sin x plus 1 over sin x over 1 minus 1 over sin x. Oh, no. Can I make one more change? Sorry. This will make it really good. It'll make it a better question. I just realised I should have made that one a minus. Let's make that one a minus. That is a better question.
Do you already know the answer?
Yeah. But yeah. That's got extra shenanigans in it. Yeah, that's right, that's that. You can take that one further because I made that a minus. Had I left it a plus, we could stop there. That's the clue. It's really hard to spot. It's a deliberately slightly awkward thing. Feels like
No.
Oh yeah, no, exactly.
there is something further you can do. And there's a whole raft of things you definitely can't do that you might be tempted to do.
Oh wait, is that?
Yep. Blue slips, sink ships. Okay, let's see what you've got. Don't worry, if you've just got rid of it and gone, what's he on about? Why is there an extra twist? Yeah, loads of people have done the first step. Loads of people have, which is great. Loads of people have done the bit that we've been practicing, and I put an extra twist just to be awkward. Right, we want to get rid of the sin x, so we are going to, on the denominator, so we're going to multiply top and bottom by sin x. So multiply top and bottom by sin x, put times sin x there, put times sin x there, and I end up with this. I end up with sine squared x minus 1 over sine squared x. Sorry, not sine squared x, sorry, sine x. Whoops. Minus 1. Now, that is all we've been practicing. But there is a twist. There is something else you can do. There are also certain things that you definitely cannot do. Here are some things you definitely cannot do. You cannot cancel the minus 1s. That's the same thing that we talked about before that you can't do. You can't say, oh, I've got a sine squared. It doesn't look like a squared there, does it? That looks like a 1. Let's change that so it looks more like a squared. Oh, I'm not sure I'm helping the situation. I'm making it worse. Yeah, that'll do. Okay, you can't say I've got a sine squared there, I've got a sine there. I can cancel it and make it a sine, and then that one disappears or anything like that. Those things you can't do. But what you can do, and this is something that we're going to be looking out for, and often in these show that and prove that questions, if you're stuck, it will be because you've missed this. If I say difference of two squares, does that mean anything to anyone? It means something to someone. There we go. Difference of two squares is when we've got things like this. If you've got x squared minus 9, that's something squared takes something squared. When you factorise that, what's the form of that takes when you factorise it? Go on, Rick.
Square root of the first thing plus the square root of the second thing, and then the square root of the first thing minus the square root of the second thing.
Yeah, so what you end up with, square root of x squared is x, square root of 9 is 3, you get x plus 3 and x minus 3. Okay, so whenever we see things like that, if we saw y squared take 16, we'd end up with y plus 4 and y minus 4. If we ended up with 4x squared minus 100 y squared, we'd end up here with 2x plus 10y and 2x minus 10y. So we're looking for things where we've got something squared take something squared. And 1 is a squared number. So it's less obvious than like a 9 or 100 or a 25, but 1's a square number. So this is something squared takes something squared, which means, and this is why I had to change it to a 1 so I could raise this point, we can factorize this to sine x plus 1 and sine x minus 1. And then, because we've got a sine x minus 1 on the bottom, and that was the clue to look for a difference of two squares. Whenever you see like a sine x minus 1 or a sine x plus 1, not a sine squared, a sine x minus 1 or a sine x plus 1, think, oh, maybe there's a difference of two squares sort of situation going on. Now, those two can cancel, and I just end up with sine x plus 1. Okay, so that whole last bit there, that's not to do with what we're doing with the fractions, but it was an opportunity to highlight something that's going to crop up a lot in these prove that questions. All right, fab. So let's do some prove that, show that questions. At the end of these, if you want to, at the end of each of these questions, you get to write QED, and because I can never quite remember what it stands for, that's what it's from. It's basically Greek for going, that's what I was meant to show. So if you, at the end of the proof, you can write QED if you want to. You don't have to. It's quite nice. Something that I'm going to say about these prove that and show that questions is it's very important how you set them out. Okay, we're going to do a couple of examples. We're going to start with these three here. These first two just say simplify. You're just given an expression and you're asked to simplify them. Keep the whiteboards out, because I think for most of this I'm going to ask you to try out the whiteboards and then we'll go through it, because I think the getting stuck, getting lost, getting a bit, oh, I don't know how to do these, is part of learning how to do these ones. If you remember from, I don't know how many of these you did last year, they're much more of the year 13 than the year 12, but these are, sometimes in maths you have questions where you just follow a recipe. Like those ones where we're solving before, basically you do the substitution, you rearrange the quadratic, you solve the quadratic, you find the trig solutions. It's, it's on rails. You kind of know what you're doing. Bang, bang, bang. These show that questions are a little bit more, ooh, I might do this. Ooh, what's the next step? And for some people, that feels a little bit uncomfortable until you practice more of them. The flip side of it is once you got these right, they're more satisfying because they're a bit more like a puzzle. Okay. These first two were just us to simplify the expression. This last one, where it says prove that, we're going to set those out in very, very specific ways. And there's some bad habits that some of you might be tempted to do, but I want you to be very careful about how you set those out. And I'll say it now, but we'll go through it again at the time. What you're going to do is you're going to take one side of this and manipulate it until you get the other side. You don't manipulate both sides at once. So when it's a prove that and it's an identity, so when it's got that that triple equal thing, which means these are equivalent to each other. It's not just they're true for some values of theta, they are true for every value of theta. That is just that in disguise. When you're asked to prove those, you take one side and you do things to it until you get the other side, and at the end you go QED, or equals left hand equals the right hand side, or equals the left hand side, and that basically you'll say.
Last year, but not with cos and sine and all that.
Yeah, so we'll do, it's a lot more. It's not really on the spec for AS. We just get you started on last year, so because it takes a little while to get in the habit of it. Okay, so we are going to do some of these that end up using these identities, but the first ones we're going to do are largely just going to be involving sine and cos. So even though they've got cos and cosec and sec in them, most of these first ones, the trick to doing them are going to be to change everything into sine and cos, or possibly the odd tan, and then play around with them. Probably it's going to end up being next lesson now. We'll do some that need those identities as well. Okay, so let's have a look at this first one. What I'd like to do, have a go on your whiteboards, and then you can get it in your book. Can you simplify sine theta, cot theta, sec theta? And like I said, the trick for that is going to get them all in terms of sine and cos. The reason we know that's going to be the way to do it is because we're looking at, we're going, well, we've got a sine, we've got a sec, we've got a cot. Really, there isn't a single identity that links those, but if they're all in terms of sine and cos, some things might cancel out. We're not sure what's going to happen, but it gives us a start. It gives us something where something might happen that ends up looking a bit more simple. So yeah, we're going to change them all sine, cos, and tan. Sine and cos, and then see what happens. See what we can manipulate that into being. And I think with cot, I get in the habit of, rather than exclusively thinking of it as 1 over tan, if you start to see it as cos over sine as well as 1 over tan, I think it's useful to have.
Cos over sine, yeah.
Yeah, so because it's tan flipped, it's cos over sine. If you're having both of those in your head, seeing it as both things, I think is quite helpful. Yes, you can go further. Oh yeah, you have. Yeah. I missed the your little box. A little bit longer. This one does simplify quite nicely, so if you've done it right, when you get to the end of it, you go, yeah, that's simplified correct. So. So sine theta, cot theta, sec theta. I'm just going to go through it slowly, so if you're still working on it, that's fine. I'm just going to write them all. Oh, it's on. Thank you. If front row, if you be freeze monitors, that would be great. Just let me know whenever I do that, every single time. Cos theta over sine theta for cot, and sec is 1 over cos theta. Now, once we've got to that point, look, we've got. You can, if you want to, write it all over a single fraction. So you can write it as sine theta over cos theta, and the bottom would then be sine theta over cos theta. You don't have to put this line in if you can already see what's going to happen. But as soon as you write it like that, you can see what's that going to simplify down to.
1.
Yeah.
I did a different way, just to put 1.
What did you do? Did you write that first line, the sine theta plus cos theta?
No, I got sine theta times 1 over tan.
Yeah, that's fine. Yeah, because 1 over tan is just sine of 1 over sine over cos. What did you do once you? Oh, did you do then you had sine over cos times 1 over?
Yeah, so it's
Yeah, that's fine. Totally fine. Nothing wrong with that at all. Right, have a go then at the second one. It's another simplify. So same sort of idea. Have a go at that one, and don't worry about that. That is not the one you're doing. That's just a blank paper that I happen to upload. Yeah, that. Honestly, that's not the paper because that's not got any mechanics on it. You can go away and do that if you like, and thinking you're being all sneaky, but it's definitely not that.
Yeah, I was going to say if it was the paper.
Yeah. Wow.
No, it's
The reason it was open is because I was looking at how many marks the old paper used to be.
Oh, so that is the actual paper.
No, it's not. No, I just opened any old. Do it. I mean, it's not going to harm you. You're doing a bunch of maths. It was what was it? 2017 Core 1? Can you get it? What was it? 2005. 2005. Can you get it from the Maths and Physics website? Maths and Physics tutor website?
Really?
Go on, I dare you to do that. Have I gone too far? Is that-
That's proof it's not the paper.
Should be. Should.
Okay, how are we doing with this one? We getting anywhere? So we're going to start as close to 20 past as we can.
Wait, it's down. You say it's now.
Yeah, well,
It's in 5th period.
no, it's so today it's after school. Tomorrow we can start 5th period because today.
So tomorrow is good. Yeah.
Tomorrow, yeah, Wednesday we can do 5th period. No, because it's today it's straight after school. Tomorrow it's 5th period. Or tomorrow if you can't do 5th period, you can start after school. That's fine. We can have up to 2 different stuff. Right, okay, folks, how are we doing? How are we doing? We getting anywhere with this one? Yeah, you've slightly overcomplicated that. Keep it as 2 separate terms. Okay, so let's see what we've got. I would be tempted with that to write it as, I'm going to leave this sine theta cos theta for a second outside the brackets. Sec theta is 1 over cos theta. Cosec is 1 over sine theta. Now, I understand why you might be inclined to add those, because if you've got fractions, the temptation often with these is to add them. But we were asked to simplify it, and if we just multiply these out as 2 separate terms, first of all, let's see what we get. We get sine theta cos theta over cos theta, and we get sine theta cos theta over sine theta. And this first one, will simplify down to just sine theta. And the second one here will just simplify down to cos theta. So you just get sine theta plus cos theta. That's all good. Okay. So, those just said simplify. This next one says prove that. And whenever you're going to do a prove that one, like I said before, you're going to take one side. It doesn't matter which side you pick, although, sorry, I'll rephrase that. You can pick either left-hand side or the right-hand side to pick, and there's reasons that you might pick one rather than the other. You don't have to just pick the one they've written as the left-hand side. You can pick the right-hand side if you think that's going to be an easier place to start. And if you pick one side and get stuck, you might want to restart the question starting with the other side. And we're going to manipulate it using what we've done, using these sort of identities until we get the other side. What you can't do is you can't multiply through. It's not an equation. We're taking one side, we're manipulating that thing until we end up with the other side. A couple of tips for doing it, and I will give you this to stick in your book. These tips will make more sense when you've done more of them. That once you've got the context of kind of like, oh yeah, I remember doing a question where I had to do this. So in order, if you have to prove that or show that an identity is true using trig identities, it can feel different to other maths questions. It can feel a little bit uncertain because there's lots of different ways to do it. There's often lots of different paths to get there. And there's not a definitive way to approach these questions. It's not like I'm going to say you always do this, then you do this, and then you do this. But instead, there's general guidelines. So, and if you try and think of them as a puzzle, as a challenge, rather than, oh, I hate these questions, that would be great. So I actually quite like these, even though they're a little bit more, not sure if I'm going to be able to do it. You always start with one side and manipulate using trig identities to end up the other side. It's often easiest to start with the side that looks more complicated, because it's often easier to start with a complicated thing and simplify it than start with a simple thing and try and get more terms out of it and make it look more complicated. There will be occasions when you look at it going, well, both sides look really complicated. I don't know where to start. In which case, just pick one, start, see if you get stuck. If you get stuck, try it starting with the other one, and it might fall out more easily one way than the other. If there are fractions, it often helps to put them over the same denominator and add or subtract them. So if you've got two fraction terms, particularly when you've got the reciprocal functions, you'll often get two fraction terms. If you're asked, if one side of the equation asks to add them or subtract them, get them over the same denominator, see what happens when you add them. And often with this, there will be an element of see what happens. It'll be a kind of, I'm not sure if this is going to get me there, but I'll do this and then neaten it up and then see if the viewpoint from that part of the question shows me what I need to do next. And that's what I'm saying here, is it sometimes helps to look ahead at the end result. So sometimes you might look at the end and go, oh, it's not got any tan x's in it. There's tan x to start with. Maybe I should get it in sine and coses because it will cancel out, for example. Or it might be that you're starting with two terms and you're ending up with one, and the two terms are fractions, so okay, that's suggesting that I should add them to get into one term. But don't be put off if you can't see the end. You're not necessarily starting these questions off going, I know exactly what I want to do. It's okay just to know what you're going to do next. So it's okay to just go, wow, I've got a bracket, I might expand it, that might help. It's all right to do that, simplify and then go, okay, now what? So it's fine to do that kind of like, as long as you're making another step, it doesn't matter if you can't really see the end of the journey. But sometimes it's worth just checking the end of the journey and kind of go, what was I aiming for again? So a balance of those two things. But don't get hung up on not knowing what to do next. If you're stuck, see if using difference of two squares can help you. So I remember from doing these from A level of countless times when I get stuck on one of these, and go, what is it? And it will be, and the teachers go, difference of two squares. And go, oh, yeah, right, I now know how to do the rest of it. And so it won't always be difference of two squares, but just, I personally remember often when I was stuck, it's because I hadn't noticed something to do with difference of two squares. And it can be like the one that we did before, where you've got a sine squared theta, take one, or it could be, if you've got, say, on a denominator, if you've got sine theta plus 1 on the denominator, what you might need to do for the next step is multiply top and bottom by sine theta minus 1. So you're bringing in the difference of two squares. That might be necessary. So you, even though there's not a difference of two squares there, you can make it a difference of two squares by multiplying by that. And then on the bottom, you'd end up with sine squared minus 1. And what's sine squared minus 1? Cos squared. So that radically changes what that looks like by multiplying top and bottom by sine theta minus 1. So that's a trick that might come up. If you're completely stuck, start again, this time starting with the other side. Okay, so I've got those tips as something you can stick in. So if you take one, pass the rest on. Don't worry if some of those tips are a little bit on the cryptic side at the moment. They will make more sense the more of these questions that you do. And here's the analogy. This analogy might not work for you, but this is the thing about knowing where you're aiming and knowing where you're not. So when I was saying that sometimes it helps look at the end for clues, sometimes it's just what step am I going to make next. the analogy is if you've got a big dark wood and you might just be able to go, well, that's the only path that I can see. I will take that step and hope it's leading in the right direction. Every now and again, you might want to climb a tree and go, oh, that's where I'm aiming for. You might want to look at the end now and again, but you don't have to always know where the end is. If there's only one path available to you that you can spot, take that path and see what happens and hope suddenly that it all clears out and it's like, oh, there's where I was meant to be. Okay? So that's like the Candy Crush metaphor in my head. That's how I picture these questions. So if nothing else, it's an insight into my brain. So what we're going to do, we're going to have a go at this one here. So what I want you to do with this one, actually, I'll give you a second to get all those cuttings stuck in. There should be some in the cupboard there. So Ruth, can you chuck some glues that way? No, don't be wandering around.
Okay, I don't wonder.
No. We're trying. Yeah, we're trying to minimise that sort of thing, so passing the things around instead. So what I'd like you to do with this one, oh, hang on, I've not written the whole question out, have I? We're asked to show that this is equivalent to cosec. No, sorry, cos cubed. Okay. So what I would like you to do for this one, which side do you think looks most complicated? The cot theta cosec over sec squared theta plus cosec squared theta. Side's looking more complicated. This side or this side? Left. I'd say the left too. So what I would tend to do to start these off, it stands for that. It's Latin for, where is it? Quod errata demonstratum. It's basically which had to be demonstrated. Especially, I've shown the thing you asked me to show, kind of thing. So if we start with, where's my blank piece of paper? If we start with this left-hand side, so what I'm going to write is I'm going to write LHS for left-hand side equals cot theta cosec theta, and if you do this on your boards, sec squared theta plus cosec squared theta, and we're going to manipulate it. We're going to do various steps, and then hopefully somewhere down here we're going to end up with, don't write this bit down yet, but this is just so we know what we're aiming for. We're going to end up with cos cubed theta, which is the right hand side. So that's what we're aiming to do, but we can only manipulate this within itself. We can times top and bottom by the same thing. We can split it up. Well, actually, we can't split it up because it's not the sum on the top.
Showing that.
We're going to show that equals that by starting with this and manipulating it in itself till we get that. So, as a hint for this one, there's two ways you could do it. You could possibly get these identities involved because we've got cosec squared and sec squared, but actually, if we do that, all we're going to end up is having some cot and some tan in there, and it's not necessarily going to help move us forward. What I think is going to be more helpful for this is because we've got cot in there, and we've got cosec, and we've got sec, if we get it all in terms of sine and cos, and see what happens, have a go at that. So write those all in terms of sine and cos. Just see what you can spot to do, and see if you can get all the steps down to doing this. Like I say, there's not a set way of doing it, but having that confidence to go, I'm not sure if this is going to get me there. I'll just start out on my journey. I reckon I'll make it. Picture yourself as your favourite hobbit going out on a little adventure. It's a long way. Even the greatest journey starts with a single step. Future there as well. I'm really mixing all the literary metaphors and
Can sec squared be written as 1 over cos?
yes, yeah. Because sec squared would be it would be sec times sec, which would be 1 over cos times 1 over cos. Yeah. So, but it's worth asking rather than just assuming. Yeah, but that's why.
Wait, why is sec squared 1 over?
So sec squared, sec theta is 1 over cos theta. So sec squared theta is sec theta times sec theta. So that's going to be 1 over cos times 1 over cos. So it'd be 1 over cos squared. But you don't have to prove that each time. It's fine to go from that to that.
What you like?
You've got. Would it have to be nothing? Would you want it to be nothing, or would you want it to be something else? I think you mean 1, yeah. I know.
How do you get that? Yeah, I understand. Comes out, and then comes out. George is unintelligent. So why?
Anyone got there?
Yes.
Hey, kids.
I was getting
Okay, so
I'm sort of
I'll give you another minute or so, and then we'll go through.
I know, put my pen on it.
Oh, so no, that's one of the sign.
Along with my other pen.
Oh yeah.
Yeah, I'm keeping this out.
Right. There's a couple of different ways of doing it. So I'll go through a way of doing it. You might have done something slightly different. So I would be tempted. I would be tempted first of all to write everything in terms of sine and cos. So this would become cos theta over sine theta instead of cot times cosec is 1 over sine theta, isn't it? And then all over a big line, sec squared is 1 over cos squared theta, and cosec squared is 1 over sine squared theta. Okay, so we've got that top line. I'm going to neaten up a little bit. I'm just going to write it as cos theta over sine squared theta, like that. Just so it's a little bit neater. That's all I'm doing with the top. And on the bottom, I've got 2 options. I could combine this into a single fraction, or I could start thinking about, can I get rid of those fractions? So what I'm going to do, actually, I'm just going to leave it as it is for now. So on this line is just about neatening up the top line. But what I'm going to do is I'm going to do what we did before on the whiteboards. I'm going to say I don't like those fractions. I'm going to multiply top and bottom by sine squared, because I want to get rid of the sine squared theta. And you know what? I'm also going to multiply top and bottom. Actually, I'll do it in 2 steps. So if I multiply through by sine squared, I end up with the top times sine squared is going to give me cos theta. The bottom, this one's going to cancel to give me 1, and this one here is going to give me sine squared theta over cos squared theta. What should I do next? Yeah, if I times top and by cos squared. Well, I could add that up in KFC, but it's easier if I just multiply by cos squared theta. Because, can you see what's going to happen on the bottom? Yeah, can you see what's going to happen on the top? Yeah. So the top is going to become cos cubed. theta. It's all getting a little squish now. The bottom is going to be sine squared theta plus cos squared theta. So I've got my cos cubed that I was aiming for, but what's going on the bottom? I've got sine squared plus cos squared.
1 equals 1.
It's 1. There we go. So it equals cos cubed theta over 1, which equals, I'm going to run out of board there, equals cos cubes. Okay, ideally you'd be going down Q, E, D. Done.
Why do we want to do that though, sir?
Why on earth would we want to do that? If we are doing maths in the wild, out in the real world. Yes,
Show off peacock feathers
Yeah,
for the media.
flexing your trigger identity.
Oh yeah, the girls are really going for that, sure.
The reason you would want to do that is if you're doing maths in the wild, if you're doing maths in real
Okay,
life.
let me ask you this.
Oh yeah. Oh,
Can you differentiate
Oh, that's
that?
oh yeah, that's.
Can you differentiate that? Can you differentiate that? Well, you should be able to.
Yeah. So now
If
you can
can't,
differentiate
then
that.
shame on you.
Right. So before we go anywhere,
Visit the bin with your litter.
visit the bin with your litter. You have got a homework that's due for Friday. Now on that sheet, it was question 6 that you were doing for Friday. I'm going to add a little bit to that. It was a question 8 that we couldn't do before. That is now a question 8 that we can do. Can you do that as well for Friday? So you've still got 5 days to do it. 3 days. What day is it? Tuesday. You've still got a couple of days to do it. So if you add that question 8 to the homework for Friday, that will be wonderful. I'll add it on the show my homework. It's what we're doing in the first part of the lesson. So it's not the show that questions, it's the solving type of questions.
Right. It's been a pleasure, sir.
Hey,
Thank you for
it's
the
all mine.
lesson.
If you pop it in there. It's been a journey, hasn't it?
Is it a slow journey, Joe?
No, quick journey.
Looking at this report, they are.
So short is on.
My dad does that and it's gone in my head.
That's
The amount of comments I get on that day.
What, ankle swingers?
Yeah, I'm
Yeah.
fashion.
You're out showing off your trigger identity, you should make sure your ankle's one side. That's
I couldn't have one without the other.
right. Yeah,
There's
so
a litter on the floor.
That was rude.
And there's a
Just-
board
That's
on
me,
the
that's me.
either after school tonight in here or from you can either do it after school or from period 5 tomorrow. It's going to be an hour and a half. It's going to be a lot of fun. See you later, folks.
Thank you very much.
So I have a free tomorrow, period 3 and period 5.
Oh, you need
Yeah,
to
we
talk
can only,
to them.
we can't do anything. Oh yeah, other than that.
Oh, in your book. Oh, okay, right, okay.
Period 3.
Yeah.
Right, tomorrow then.
Yeah.
That means I can do the test tomorrow as well.
Start period 3 and then you can do the test tomorrow. Yeah,
Perfect.
fine, thank you very much.
Where would it be?
tomorrow because I've got period 3 tomorrow.
No, period 3, that's a personal statement I'm meeting with Drew about. So
Oh,
you're saying, can we meet about personal statement in period 3?
Oh,
so
I
we
thought
don't
you
have to
meant
meet-
about
No,
test.
yeah, no, test has to be the period 5.
Okay.
But, yeah.
For the further maths homework, I'm stuck on 4 and 5. I don't know
Did we
how
have a
to
pre-test
do
for
that.
What's it say? Can you make it bigger?
So I gave you
Yeah.
feedback on
So,
the
single matrix from look at the area. So have a look at your notes. There's a link between discriminants and the
And then
area.
you did.
Oh, is it like this?
Use the discriminant to see what happened with the area.
Oh, if it's discriminant, then is it timesing it
Yeah,
with
it's not much.
Have a
So
look in
you
your
just
notes,
go through that
because it
feedback.
depends if it's 2 by 2 or 3 by 3.
2 by 2?
Yeah, okay, so
Yeah.
have a look in your notes for it. Explain whether or not the triangle has been reflected. So again, that's
Yeah,
probably the
that's-
discriminant
it's
that you
not
need
that
to look
hard.
up in your notes.
It's more of the calculating of the area
So
itself.
the area, so you know the area of the original shape,
Yeah.
yeah?
The area of the
Yeah.
image is 50.
So have a look in your
I'm not
notes.
waiting yet.
Oh yeah, sorry, yeah.
Are you coming over there?
Do you know what? I'm going to do the printer over here because I know it works. Thank you for.
What classroom will it be in tomorrow, period 3? In here?
No, period 3 tomorrow. Yeah, I'll be loitering somewhere around
Okay,
here.
so-
Yeah. Period 5 it isn't in here actually. Period 5 tomorrow. It's in just that one. Yeah, it's in just one. The after school. Yeah. So have a look at your notes because I want you to get used to doing that as a thing. Rather than that's why I'm not just telling you. I'm not just saying it to be awkward.
It's
Oh.
because
So there-
the first lesson I wasn't here, so I don't have notes of that.
Oh right. Okay.
That, if
So
it's
you-
from the
right.
notes there, then I don't have it.
So it is, if it's an area, so if it's a 2D shape, the link between them is the scale factor for area is the discriminant square. So the
Oh,
yeah, so the discriminants If the discriminant is negative, it means that. Hang on, I just need to end that.